Our final little corner of chemical reactions here is to talk about ionic equations. And ionic equations are just a different way to notate reactions that are happening in solution. So as an example, let's start with this reaction here between aqueous sodium carbonate reacting with a solution of silver nitrate. And so see if you can go ahead and set up a balanced chemical equation for this chemical reaction. Go ahead and pause the video while you do that. Okay, so hopefully you recognize it was a double replacement reaction. Sodium carbonate is Na2CO3. Silver nitrate, silver is a 1 plus ion, nitrate is a 1 minus, so you get AgNO3. And so this is a double replacement reaction. You're going to switch partners there. The silver is going to go with the carbonate, the sodium is going to go with the nitrate. Sodium's 1 plus, nitrate's 1 minus, so you get NaNO3. Carbonate is 2 minus, and the silver is 1 plus, so you're going to get 2 silvers. You're going to need to double the sodium because you have 2 on the left and 1 on the right. And then you're going to need to double the silver nitrate as well to account for those 2 silvers on the right. So 1, 2, 2, 1 as it is written there. And so hopefully you also remember to check your solubility table. And silver carbonate is not a soluble substance, so that's going to produce a precipitate. An ionic equation lets us see the real kind of processes that are going on here. And so what we're going to first do is write a complete ionic equation. Anything that is AQ, we're going to break it up into its ions. And we're not going to worry about at this point how many of those ions we have. We're just going to identify what types. So for instance, the sodium carbonate is made up of Na plus ions and CO3 2 minus ions. And so you're going to write those separately because when you dissolve an ionic compound in water, it breaks apart into its individual ions that are then going to solvate throughout that liquid or that solution phase. And so this is what a complete ionic equation would look like. Sodium ions, carbonate ions, silver ions, and nitrate ions. And we'd essentially start with maybe 2 different beakers that have these 2 solutions in it. So one of the beakers would have sodium and carbonate ions, the other beaker would have silver and nitrate ions. And then we would mix these 2 beakers together. And when that happens, the sodium and the nitrate ions, which are still soluble, are going to still be in that AQ form. They're going to look exactly the same. But when the silver ions bump into carbonate ions, they form silver carbonate, and silver carbonate is insoluble. And so what we do at this point, notice then the silver carbonate is not broken into ions because it's going to precipitate out as a solid. And what we do at this point is we try to identify what are called spectator ions. Spectator ions are any ions that appear the same on both sides of the equation. So from a chemical reaction standpoint, they're not really doing anything, but they are very important. They're important because most chemical storerooms do not have jars of ions. Chemical storerooms have jars of ionic salts. And so the sodium's job is to bring the carbonate to the party. The silver or the nitrate's job is to bring the silver because there are no jars of carbonate ions or jars of silver ions generally in a laboratory storeroom. There are salts of various elements, and then you have to dissolve those in water to get at the ions. So the spectator ions are carriers of the elements that end up forming the chemical reaction. So our spectator ions in this case are sodium ions and carbonate ions. Then we're going to write what's called the net ionic equation. The net ionic equation is what's left over after you cancel out the spectator ions. And what you get is carbonate ions reacting with silver ions to produce silver carbonate. I just noticed that I wrote carbonate ions in my spectator ion. It shouldn't be carbonate, it should be sodium and nitrate. So I'll fix that in post-production, as it were. So you're going to see a nitrate there. So when I say it said carbonate, we'll fix that before we post it. All right, so the net ionic equation then is the carbonate ions reacting with the silver ions to produce an ionic bond. And so the net ionic can reduce us down to the basic chemical process that's taking place, and in this case, it's the formation of a chemical bond. When you're working with ionic equations, you always need to make sure you balance for ions and charge, or sorry, for atoms and charge. So we have one carbonate on the left and one on the right, so we're in good shape there. We have one silver on the left, but two on the right, so we're not in very good shape there. Also, the charge on the left would be 1 minus. You got to have a 2 minus and a 1 plus. And the charge on the right is neutral. So for both of those reasons, we're going to need 2 silvers. And if you go back up to our original balanced equation, lo and behold, you have a coefficient of 2 on the AgNO3, so it's exactly what we would expect. So let's take one more stab at it and write a complete and net ionic equation and identify your spectator ions for the following reaction. Zinc metal reacting with silver nitrate solution. Go ahead and pause the video and take a shot at it. Okay, hopefully we recognize this time we have a different type of chemical reaction. This type of chemical reaction is a single replacement reaction. You're going to want to check your activity series to see if zinc can replace silver, and zinc is in fact above silver on the activity series, so it will replace it. Zinc forms a 2 plus charge, silver forms a 1 plus charge, so that means you're going to need 2 nitrates in your products to form zinc nitrate. And then we'll balance it 1, 2, 1, 2. To get the complete ionic equation, anything that's AQ, we're going to break up into its ions. So notice I left that zinc solid without a charge on it, but the silver and the nitrate break into ions. The zinc nitrate on the right side breaks into ion, but the Ag solid has no charge because it's in its elemental form. Then we want to sort out the spectator ions, and in this case the spectator ion is the nitrate. The nitrate brought silver to the party so that silver and zinc could interact. And so what we have is we have a zinc reacting with 2 silvers to produce a zinc 2 plus and 2 silver atoms. And if you look at what's taking place here, what you get is a transfer of electrons. Zinc starts as neutral, the silver starts as charged. Zinc loses 2 electrons, 1 to each of the silvers. So when each of those silvers gains an electron, they become atomic silver, and there are going to be 2 of them. Notice the balancing is 1, 2, 1, 2. Before we balanced, we had a zinc and a silver on each side, but the charge was not balanced. Without the 2 in front of that silver on the left side, we were at a 1 plus charge. Without the 2 on the silver on the right side, we were at a 2 plus charge. So you need to make sure both atoms and charge are balanced. Again, it shouldn't be surprising that we have a 2 on that silver, because when we look at our original balanced equation, the coefficient on the silver was 2. And so we've looked at 2 different kind of types of ionic equations that kind of led us into kind of the base chemical process that's taking place. In the first one, we looked at the formation of an ionic bond, and in this ionic equation, we're looking at a transfer of electrons between 2 different metals.